objective of this assignment is to know what capillary pressure is and how to measure it, to know what relative permeability is and how to measure it, to read the graph for both virgin method and Pearson method. Next, what is capillary pressure? Capillary pressure is the difference between the pressure of the non-wetting phase and the wetting phase across the interface of two immiscible fluids. The formula that we will use to find capillary pressure is PC equals to PNW minus PW, where PC is the capillary pressure, PNW is the pressure of the non-wetting phase, and PW is the pressure of the wetting phase. How to measure capillary pressure? We have three techniques to measure capillary pressure. The first one is porous plate technique, PP. The second one is mercury injection capillary pressure, MICP. And the third one is centrifuge. We will look into the first technique, which is porous plate technique, PP. In this technique, a porous disc saturated with one fluid, for example water, is placed in contact with a rock sample saturated with another fluid, for example oil. Pressure is gradually applied to one fluid until equilibrium state is reached. The capillary pressure is determined by the applied pressure and the difference in fluid levels. The second technique is mercury injection capillary pressure, MICP. In this technique, mercury is injected into a dry rock sample under increasing pressure. The volume of mercury injected at each pressure step is recorded. The pressure at which mercury starts to enter the pores is related to the larger pore throats, and as pressure increases, progressively smaller pores are filled. This method provides a capillary pressure curve which is used to infer pore size distribution. Lastly, centrifuge. In this technique, the rock sample saturated with two fluids is placed in a centrifuge. The centrifugal force causes the fluids to separate, and the capillary pressure is determined from the radial distribution of the fluids and the applied centrifugal force.
Relative permeability is the relative ease for one fluid to flow in the presence of another immiscible fluid within a porous medium. It compares the effective permeability of a fluid to the absolute permeability of the rock. The value can range from 0 to 1. A hydrocarbon reservoir can have oil and water, gas and water, and gas and oil, and water present at its pore spaces. Therefore, relative permeability is considered to be a transport property that helps in estimating oil production when another fluid is injected. So when we discuss relative permeability, there are three parameters that needs to be discussed. The first is relative permeability, the second is absolute permeability, and the third is effective permeability. There are two methods in measuring relative permeability. The first method is by using a steady state approach. This is when both fluids are injected simultaneously. The flow rates and pressure drop are measured to find the relative permeability. Then, we can calculate relative and effective permeability. After that, the injection rates are changed to obtain a new set of relative permeability. The system needs to reach a steady state regime before any reading can be taken. Steady state relative permeability is considered more accurate than the unsteady state method, which is covered in the following section. However, the steady state method is more time consuming. The figure shown is a schematic of a steady state water flood relative permeability experiment. The second method is unsteady state. In an unsteady state measurement, or also referred to as displacement method, the rock or the core is saturated with one fluid, water or oil, and then the other fluid is injected to displace the first fluid. During the unsteady state displacement, the time is recorded for flow rates of both fluids. Applying this method is cheap and relatively quick. However, this method requires analytical interpretation of the result. That is because relative permeability is not measured directly, which makes the result less reliable than the steady state method. The figure shown is an example of schematic of an unsteady state water flood core flood relative permeability experiment.
For the result, we need to take sample from 22.1 data set, and we choose Virgin approach and Purcell approach. For Virgin approach, firstly we take mean saturation and capillary pressure in PSI unit that we need to convert it first, and plot the graph mean saturation against 1 over PC square, and then we need to plot the graph mean saturation against relative permeability for wetting and non-wetting phase. To calculate KRW, we need to calculate absolute area KW using trapezoidal method, using trapezoidal formula, because the integration part is done for area under the graph. And then we need to find total CD ratio for KW, which is water saturation minus minimum saturation, which is 0.187 divided by 1 minus 0.817. Minimum saturation is apply for irreducible water saturation. And then we need to square total saturation ratio before multiply with effective area for KRW and divide with K absolute, which is summation area from each 6 interval that we have. It is applied same goes with K and RW. And then we apply same formula but only differ in terms of totality for the K and W, because we need to 1 minus water saturation and minus equilibrium saturation, which is 0, and divide by 1 minus 0.187 minus equilibrium saturation. The graph, it represents inhibition because of the non-wetting phase replaced by wetting phase. Okay, for the Bessel method, we also plot the same graph, which is mean saturation versus 1 over Pc square, and second graph, which is mean saturation against relative humidity for wetting phase and relative humidity for non-wetting phase. The only difference from Berdine method is we don't need to find total city ratio for effective humidity, water saturation, effective humidity, wetting phase and non-wetting phase. So we just need to find K absolute, which is summation for each interval using trapezoidal formula, and find the area under the graph for wetting phase and non-wetting phase. So we need to divide. The graph also show inhibition because non-wetting phase is displaced by wetting phase. We conclude that Bessel method is better than Berdine method because for the Bessel method, the summation of the wetting and non-wetting phase relative humidity at a specific saturation is 0, which is not true for the porous medium. And the Berdine method, wetting phase relative humidity fits the experimental data much better than the expression for non-wetting phase.